Welcome to session 7 of day 2 of the 2025 RNG Technical Symposium. In this session, we're going to hear from Unconventional Gas Solutions about their biogas offering, including exciting things like their 4-stage membrane approach to gas upgrading and hydrogen sulfide removal from biogas through membranes. So you know the drill. You can ask questions in the chat of the Q&A box as we go, and then we'll have time for questions at the end. So with that, I'd like to introduce Justin Billing, Senior Applications Engineer with UGS. Justin has extensive experience in biomass conversion and renewable energy. He's served as a U.S. National Team Leader for Task 34 of the IEA Bioenergy Technology Collaboration Program. Most recently, he was Director of Chemical Engineering for Circlia Nordic APS, a Danish bioenergy startup company. Justin has over 20 years in research and technology development in the bench and pilot scale with a focus on physical and chemical separations, including 14 years at the Pacific Northwest National Laboratory. So, Justin, welcome, and the floor is yours.
Yeah, excellent. Thank you for the introduction. I'll go ahead and put the slides up here. PowerPoint, share screen. Everything good? Look good? Excellent. So today's presentation is Unconventional RNG. We're looking at membrane solutions for cost-effective H2S removal, high methane recovery, and preparing the permeate stream for CO2 liquefaction. A little bit of company history before we get into the rest of the presentation. UGS was incorporated in 2013. We have always been and continue to be a technology-based company. So we package membranes, but we're more than a membrane packager. We develop membrane technology, and also some of the other technologies that we offer are our own designs. And that comes from the earliest time in our history. The membrane, the Porogen platform, was acquired by Air Liquide in 2015. And at that point, we began as a company packaging membrane systems for Air Liquide. That continued until 2019 and into 2020 and 2021. Currently, and so we transitioned from the Porogen also into Air Liquide's biogas upgrading plants and continued to package biogas upgrading plants for them. From 2019 to the present, we focused primarily on dairy biogas and landfill gas upgrading systems and are packaging our own systems with UBE membranes. Currently, we have about 37 references of packaged systems between those we've packaged ourselves and also with Air Liquide. Our key experience is both the capabilities and our technology. So we're an emerging leader in designing and fabricating gas separation technology packages for the energy transition. We bring oil and gas and offshore design principles into the field of biogas to make really robust systems and designs. The fields that we're active in, I mentioned, is biogas purification. We also do hydrogen purification, CO2 or CO, syngas type separations, helium purification systems, natural gas sweetening, nitrogen generation systems, and offshore work. The technologies that we use are membranes, adsorption, so PSA, temperature swing, pressure temperature swing, vacuum pressure swing, compression dehydration, deoxos. We also do the automation and controls. And I do want to also highlight our on-site services. We operate a real strong service team at startup and commissioning to make sure everything goes well and we have a successful commissioning and support basically everything that we build. In biogas to RNG, we offer fully integrated end-to-end packages, including PLC and HMI programming. all of the instrumentation and controls, skid-mounted systems such as you see in these photographs, membrane-based CO2 removal systems. We use media-based H2S treatment systems, and as we'll also see later, membrane-based bulk H2S removal, which is a unique technology or approach developed by UGS. We also provide compressor packages. Not all suppliers of membrane separation biogas upgrading systems package or have the ability to package and integrate their compressors. That's something that we offer. And in addition, we have our own design for a deoxygenation unit that has a lot of exciting features, a lower reaction temperature due to a more active catalyst, and improved, more rugged metal materials of construction. And for the balance of plant, we can offer like a tempered glycol cooling system to manage and reuse heat within the biogas upgrading system. So to kind of share compressor heat around the plant, we've designed and built those systems. And we can also add and integrate instrument air thermal oxidizers and flares. So some of the results, the proof of our design and building is that UGS systems provide high uptime and reliability. This is what our key customer in the dairy biogas field appreciates most about working with UGS is the uptime and reliability of the systems we supply. So as of 2023 and 2014, we commissioned 4 biogas upgrading systems at sites developed by Novia RNG in the range of 400 to 700 SCFM. These plants are 2-stage membrane systems with the bulk H2S removal via membranes, which we'll talk about in the next couple slides. And one system includes a deoxo with TSA dryer. Novia's superb project management and coordination with the farmers and biogas digester suppliers and degridding, manure collection, all of the above enable swift project execution. They are able to develop these plants from start of construction to injection within 12 months, and we're able to support them in that. And current commissioning times on the gas upgrading portion, so our portion of the scope, are down to 1 week. We have done 4 of these in the last 2 years and have really gotten, swift at getting them online and injecting into the grid. As of the most recent month and for the past 3 months, the 4 plants have each and collectively averaged over 99% injection into the pipeline. That is just minutes injecting into the pipeline over minutes per month. If you follow Novia RNG on LinkedIn, they give a monthly update. And so it's always exciting to see everything is in good shape. So what are some of the strategies for success for using gas separation membranes? Pre-treatment is the key to long-term performance. So we focus on several things. First of all, lowering the dew point through chilling and coalescing any oil and water drops, then superheating by 30 degrees Fahrenheit, and then VOC removal in the dairy application with activated carbon. Secondarily, system startup and sequence is important. Rapid pressurization can lead to oil carryover and dusting within the system. So we have pre-pressurization lines at smaller diameters to pre-pressurize and bring the membrane system up to pressure first before opening the main valves to the membrane skids. And we also have a programmed step to sweep the moisture out of the compressor during shutdown. So this extends the life and performance of the compressor. Also, when we package compression and membranes together, we can unlock innovation like bulk H2S removal in the membranes, which is what we'll discuss next. So This strategy of using membranes for bulk H2S removal was developed several years ago, and Novia RMG, as I mentioned, has been the pioneered this concept with us, and it's operating successfully in all 4 of the plants that I've mentioned, with more in the pipeline in the works. So in this situation, rather than having large solid media vessels or perhaps a biological H2S removal system at the upfront part of the plant before primary compression, we hardened the materials of construction by using 316L and duplex steels through primary compression, pre-treatment, and the membranes to prevent corrosion with the H2S, the sour gas that's going through those systems. The trade-off is that you can basically direct 90% of the H2S to permeate with the CO2. So H2S readily permeates with the CO2. And the first stage, so the first stage permeate will then go to the thermal oxidizer. If air permits are sufficient for both the flow rate and concentration of H2S, so that sort of the Clean Air Act Title V threshold of 100 ton per year of criteria pollutants is not exceeded, then that can be one option. On the next page, I'll show you an option with a biological scrubber, or I guess a H2S scrubber before the thermal oxidizer. And then at the end of the plant would be H2S polishing, as basically the first stage, second stage membranes reject most of the CO2, but not all of it. So some remains. To get to pipeline grade, a smaller solid media bed is required. But it dramatically saves on it saves CapEx, but it mostly saves OpEx on and labor for frequent media exchanges and the extent and amount of media purchased.
Justin, real quick, so just so we kind of understand this, so the first membrane, the CO2 permeates, the H2S and the CH4 stay behind as retentate, right?
Yeah.
Okay, so then membrane 2, the retentate again is H2S and CH4, so the permeate is what in membrane 2?
It's CO2, but it's a what we say is a more permeable membrane, so it makes sure to permeate all of the CO2, but it also permeates some methane to make sure you get all the CO2 out. So that is what's recycled back to the compressor. And that's also a high H2S stream. Whatever H2S does not permeate in stage 1 permeates in stage 2. And then a small amount of H2S is residual in the product gas. So the dashed line is basically the membrane. And yeah, so the permeate is...
So if I've got 2,000 ppm of H2S in my raw biogas, the H2S going to this final polishing vessel is what, 4,000 to 6,000 or something, or what would that be like?
So it'd be actually dramatically reduced. It's more like 200 to 400 ppm going to the polishing vessel at the end. So 90% of it either through recycle or, basically the permeate of stage 1 to the thermal oxidizer has high H2S.
Okay.
Like
So a lot of
10,000
it permeates and goes to the thermal oxidizer. Very well. Okay.
Yeah. So that's
Thank
the
you.
outlet. And then the 10% that's left goes to the polishing and the product. So
very helpful. Thanks. Okay.
Yeah, perfect. Thanks. So in the case where the volumes, either the gas flow rate or volumes or the concentrations are too high to send H2S to the thermal oxidizer, which creates SO2, which is a criteria pollutant, one could place the bulk H2S scrubber in between the membrane permeate and the thermal oxidizer, the ultimate pathway for that gas. There are some advantages of placing it there versus up front. One is that it's a lower gas flow rate since it's only treating about half or maybe 40% of the gas, as it's the CO2 portion. And since there's no limits on oxygen, most either solid media or biological or even the like liquid redox systems work better with additional oxygen to help oxidize the H2S as part of removing it or oxidizing it to elemental sulfur. There's no constraints on relative humidity, similar as oxygen. So you could add air into that scrubber as needed to make sure you get the highest capacity out of it. And also the typical pipeline specification of 0.25 grains or around less than 4 ppm is not required at the outlet of the scrubber, as in the case of if it was like on the mainstream, on the main methane stream, you would have to reduce, remove all the H2S. In this case, you could leave 50 or so or 100 ppm and combust that rather than the whole amount if needed. So basically the severity is reduced. So it would lead to better cost performance of that H2S scrubber there versus upfront. Now, here I would present a few slides about the 4-stage membrane configuration. We have to think about where this configuration works, what it's for, what it's best for, and because I don't want to, in presenting different or advanced technology options, to do away or detract it all from the fact that the majority of membrane systems that we have supplied are 2-stage systems and 3-stage, and so each one has its value and its application. So what the 4-stage membrane configuration is for is advanced applications where some form of liquefaction on the methane stream is required. You can get there with membranes only, not membranes plus amine or membranes plus something else to get the CO2 real low. Actually, by configuring membranes correctly, you can meet the criteria for liquefaction. And at the same time, you get enhanced methane recovery, same as for 3-stage. By having that extra stage on the permeate, you can basically wash and recycle all of the methane so that what exits is a low methane CO2 stream. And I have a diagram on the next slide to lay it all out. So what we're aiming for here and why you would want low CO2 concentration, one is to support a traditional NRU VPSA. They perform better with lower CO2 concentrations. Also, if you can get to very low concentrations, as I mentioned, it sets up cryogenic NRU, which is a good fit for large flow NRUs, or also if the intent is to liquefy the biomethane, low CO2 is required. And as I mentioned, the high purity CO2 product sets up liquid CO2 production. So here's the diagram. There's a lot going on here in this picture, so I'll just walk through. I don't know, does my cursor show up on the screen here? Probably not, because I'm not sharing the screen, I'm sharing the
It does a little bit. In the lower left-hand corner, there is a cursor feature. If you click it.
Okay, yeah, here we are.
Yeah.
Perfect. So I have the biogas coming in, same as before, into compressor number 1, enters the 1st-stage membrane, and we'll focus on the high pressure recycle loop first. So majority CO2 permeates, it goes into the lower pressure recycle loop. The product enriched in methane goes into the second stage membrane. So this works very similar to a traditional 2-stage membrane, except that the split here is a little better, more preferential. You can let a little more methane down into this stage, which means you get all of the CO2 out, much more CO2 out in this 1st and 2nd stage to enable ultimately 50 ppm CO2 and less than 20 ppm water in the RNG product from basically the pressure side of 2 stages of membranes. Then this permeate is recycled back to the compressor and repressurized. And this upper high pressure recycle loop operates at 115 to 230 psig. The majority CO2, some methane stream enters the low pressure recycle loop and is recompressed in compressor number 2. That's to keep control over membrane surface area, membrane count. Higher pressure is fewer membranes. The permeate from the 3rd stage is where the impurities are concentrated. So this is CO2 with O2, water, H2S if any, and yeah, water, already mentioned water. Okay, so then that retentate is basically rinsed or put into another membrane stage where the permeate is recycled back to the feed of the 2nd compressor, and whatever methane is left is recycled to the beginning of the process. So this is how this low pressure recycle loop is. If you follow kind of the pattern here, on the inside of all these membranes, not permeating substantially, is the methane. So there's very little methane lost to this impurity stream. And that's the whole point of this. I think of it in terms of like a distillation column. There's sort of the stripper and the rectifier, and this is the bottom part of the column, and this is the top part of the column, which are sort of doing this reflux to, you know, bring out purest streams from each side. Comparing the 4-stage to a conventional 3-stage system, so you have to set a benchmark. So the benchmark is this set of product purities and conditions here. So it's somewhere in between. You probably, if you're using the 4-stage system, you might want to target lower than 0.1% CO2, and this might be a stretch application for a conventional 3-stage. You will use more membranes if you're targeting this type of pure CO2 purity with a conventional 3-stage system. But it's a benchmark, you know, a set of conditions. You can do the membrane simulation for each and see how they compare. So energy or power consumption, which is kilowatts per normal meter cubed of gas production. The 4-stage is slightly more efficient, although I would say the message here is that it's adding that extra compressor, limits recycle and recompression. And so then it becomes basically on par energy wise to operating a conventional 3-stage at the same conditions. The big story here is membrane surface area, which is square feet of membrane surface per normal meter cube per hour. So roughly, well, not quite twice, but you know, by up to almost twice as many membranes would be required in the conventional 3-stage to obtain the same purity at that spec. So it's showing you, as you're going to higher and higher purity biomethane, that something like the 4-stage membrane system will enable this type of separation at a reasonable cost. So the membranes required on the 3-stage system continue to go up exponentially as you go to lower and lower CO2, whereas you reach something more like a plateau with the 4-stage, or at least it's not exponential, it's more linear. Some of the advantages is you can simultaneously remove multiple impurities in one configuration and get liquefaction ready biomethane in a single step. So this is 50 ppm, less than 50 ppm CO2, and really, really dry, you know, down to trace water. Reduced membrane cartridge count versus the 3-stage system. Lower CO2 and O2 concentration at equal power consumption, and same as 3-stage, really high methane recovery, up to 99.8%, definitely above 99.5. Now I'd like to take a minute or two and show pictures and diagrams of where UGS is positioned going forward in the different markets. So this is a cutaway view of our standard biogas upgrading systems. We're making even more streamlined modular units at target flow rates of 300 SCFM and 600 SCFM. Our goal here is cost savings with no compromise on purity, quality, or recovery. And in this case, we would use bulk H2S removal upfront, not within the membrane. So this prepackaged offering would have small H2S removal activated carbon towers, similar to typical, I would say typical European biogas upgrading systems, membrane based. And also we just commissioned our first design built system for nitrogen rejection. So in addition to membrane CO2 removal and compression and other things, we are operating a vacuum PSA NRU, and we offer that as part of our landfill packages. Some of the unique things about our design are the internals for managing gas velocity and avoiding fluidization. We operated a lower absorption pressure than some of maybe the incumbent technologies in this field. Can handle up to 30 volume% of nitrogen in the feed, and flow rate can be scaled by adjusting the adsorption cycle time. Using the various rinse steps that and ways of rinsing and repressurizing, we can get nitrogen removal down to 1.5% in the product with over 95% methane recovery. And discharge pressure is per pipeline or customer requirements. This chart here shows kind of the heartbeat of the NRU. This is actual field data from commissioning, and the purity achieved according to our methane analyzers, 99.9. I think we confirmed by GC that was 98.6. In all cases, that was completely acceptable for the project and the pipeline. Here's the pictures of the NRU. On the left is the waste buffer vessel with the 5 beds, adsorber beds, then the valve skid, which is the heart of directing gas flow to the correct vessel at the correct time. Each step is sequenced and timed by software, automatically actuating valves to move the gas around through the adsorbers and the skid. On the right is a screw compressor package for the rinse gas. It's an example of our compressor packaging. A few more photos, another photo of the valve skid, the front side, or I guess the inlet side of the adsorber vessels, and example of the vacuum gas compressor, which is a flooded oil screw compressor. This site is in Boise, Idaho, and is available. You can contact us if you would be interested in viewing this location. We are open for tours. We can arrange to meet interested people there to see our technology in action. In this plant, we did compression, membranes, pretreatment, NRU, product gas compressor, reciprocating compressor. So it's a fairly complete end-to-end plant. So that's all the slides and information I prepared. Our contact for business development is Mark Pastore. He's also on this call, and his contact information is there. You can always also mail sales at ugs.solutions as well to get in touch with us. So thank you very much for your attention. Happy to take any questions and engage a little more. That's what we've shared. Thank you.
Yeah, you're welcome, Justin. Thank you. We do have some questions. So with the 4-stage versus 3-stage, less membranes with the 4, but another compressor, how are you seeing the economics of the 4 versus 3 compare, given those variables?
So the 4-stage is, because of the extra small compressor, it's incrementally more expensive. I don't have a percent adder for that. So I guess the technology comparison would be 4-stage membrane versus maybe 3-stage membrane plus a small amine unit, which would be necessary to get to ultra low CO2.
Can you stay on this slide? The
Sure.
normal cubic meters you're showing, is this biogas or methane?
I believe these are, this would be the inlet biogas.
Okay. Question on water vapor. How dry does the gas need to be coming into the membrane system?
We look for a dew point of greater than 30 degrees Fahrenheit at the process conditions. So our normal sequence is chill to 40, reheat to 70 degrees Fahrenheit. So that at any point within the membrane system, the enemy is condensed water vapor droplet, water condensing droplets on the backside of the membranes is the likely location due to the JT effect as you go from one side of the fiber to the other. But this is mitigated if you have, a healthy amount of degrees of superheat. So that's how we measure it. I'm not, without opening up a simulation, I don't know how many mole percent or weight percent water that is exactly at 200 pounds. It varies, but basically that's how we do it.
So have you standardized on the UBE membrane?
Yes. Yeah.
Okay.
We're
And what are you indicating as a projected membrane life? 10 years, more or less?
yeah, as we often say, it's either 10 minutes or 10 years, depending on how the pretreatment is. If the pretreatment's no good, then the membrane won't last very long. But if it's treated well, yeah,
That's very
we say, yeah, up to 10 years, we would project for our customers, definitely to plan conservatively on at least on 5. If, yeah.
okay. Here's one for you. Can H2S separation and CO2 liquefaction be done together in 4 stages?
Interesting. I would certainly have to think so. That would be combining,
We got a
basically,
stumper.
yeah, bringing the H2S into this 4-stage configuration.
Yeah.
And well, then CO2 liquefaction, which would be separate. I'm assuming H2S would be a major impurity in liquefied CO2. So some sort of scrubber or treatment would be necessary for that. It would be commingled with the CO2.
So some additional context is coming in on the 3 versus 4 stage system. UGS uses an extra compressor also for the 3-stage membrane to allow for better recovery and easier controllability. So
yeah,
more membranes for the 4-stage by maybe about 20%, but less complexity.
yes.
Okay. Final question, how does the 4-stage work in context of NRU for landfill applications? Does the 2nd stage retentate still go to the NRU, or is it the 3rd stage?
It would be the 2nd stage. So the RNG stream, if that was still high in nitrogen, then that would still go to the NRU at that point.
Okay.
So in membrane, hollow fiber membrane systems, nitrogen and methane are difficult to separate from each other to get much. So they tend to stick together through the process. CO2, H2S, water permeate readily and separate readily from methane and CO2, or methane and nitrogen rather. O2 is kind of somewhere in between. UBE membranes happen to have a little more higher permeation for O2, so you can achieve a slightly better O2 separation with the UBE membrane. So it's possible with using UBE membranes and a standard PSA NRU that you would end up meeting pipeline specification for oxygen if it's the more typical specification of 0.2% oxygen. If it's lower, then you still may need a deoxo. So that's there's enough of an advantage to make us and make others do a kind of a second look at the UBE membranes. It's, they get a little extra oxygen separation there. So
Are the UBE membranes facilitated transport membranes?
I guess I'd have to call in a lifeline from Mark Straub if he's available, our president. I know he's
He's been in touch with me here, so maybe Mark will opine on that one. I don't even understand the question.
Facilitated transport, is that like in terms of a sweep?
I don't know. I honestly don't understand the question. So we're both. But Mark wanted to offer up, UBE also has a higher selectivity for N2 and O2 versus CH4 over other membranes.
Yeah.
So we do not enrich N2 and O2.
Yeah.
Okay. This has been great. Thank you very much, Justin and UGS. We appreciate your contributions and your time, and thank you again. So slides will be on the website tonight, and with that, we will let you roll. And in 24 minutes, we have biogas to SAF coming up. So we can look forward to that as closing out the symposium. So we'll catch you later, Justin.
Excellent. Yeah. Thank you, Paul, for providing this platform and opportunity for the community. It's really great.
Yeah, good. Glad you could join.
Yeah. Thank you.